Welcome to CG Radio Made Simple. I am so glad you're joining us today because, well, this deep dive is really for you.
Yeah, especially if you're the kind of person who, just loves finding those hidden connections in the world.
Exactly. We are looking at a really fascinating blog post from 2026 by GAM000222. It's from gam0022.net. And it reveals this mind-bending mathematical secret connecting two totally different technologies that you probably use every single day.
Right. Things you wouldn't ever put in the same sentence normally.
Okay, let's unpack this.
Ah,
Imagine you're trying to find the absolute best pizza recipe on the internet.
a noble quest.
Right. You type it into Google, hit enter, and boom, perfect results populate right at the top of the page.
Thousands of them, sorted perfectly.
Yeah, no, switch gears entirely. Imagine you're playing this massive blockbuster video game. You stop your character just to look at the way the simulated sunlight perfectly filters through, like a glass of water on a digital tavern table.
Oh, those hyper-realistic, shimmering shadows across the wood.
Exactly. So here is the hook. What do finding that specific website on Google and rendering that photorealistic light in a video game have in common?
Well, on the surface, absolutely nothing.
Literally nothing. One is, it's organizing a near infinite library of human text and hyperlinks.
Yeah.
And the other is simulating actual physics bouncing light in a 3D space.
Yeah, they feel like completely different scientific disciplines. But under the hood, they are powered by the exact same mathematical miracle.
Which is just wild, comparing the entire internet to literal physics. So where do we even start with this?
Well, to really appreciate the connection, we have to look at the huge mathematical hurdles both of these fields were slamming into back in the early days.
Okay, let's start with Google then.
Right. So Google relies on an algorithm called PageRank, and its whole job is to identify the most important pages within this massive, tangled web of cross-referenced websites.
Just a giant maze of links.
Exactly. Then, on the other side, in computer graphics, you have a technique called ray tracing, or specifically path tracing. Its job is to compute the accurate brightness, the radiance of endlessly bouncing light in a 3D environment.
So sorting text based on human preference versus calculating the physical trajectory of light. I'm struggling to see how those are fundamentally the same problem.
The connection is in the algorithmic structure. Both domains deal with networks of influence, and
Okay.
they both run into the exact same mathematical brick wall.
Which is what?
An endless recursive maze, a total chicken or egg scenario.
Oh, right. Because to know the answer to the equation, you already need to know the answer to the equation.
Precisely. Let's look at the PageRank dilemma first. This goes back to Larry Page's 1998 mathematical trap.
Right. The core idea is that a page linked to by other high-ranking pages should also have a high rank.
Makes sense intuitively, right? But mathematically, it's a nightmare. To calculate the exact rank of, say, page A, you have to know the rank of page B because page B links to it.
But to know page B's rank, you need the rank of page C. And so on, forever.
Exactly. It's a self-referential loop. The formula for a page's rank actually contains the rank of the linking pages inside of it.
So you literally cannot compute the left side of the equation without the right side.
But the right side requires the left side to already be solved. If a computer tries to calculate this exactly for the whole web, billions of pages, it just chases its own tail endlessly.
And taking that exact same mathematical nightmare and applying it to physics gives us the fundamental problem of 3D rendering.
You got it. In 1986, James T. Kajia introduced the rendering equation, and it poses the exact same trap.
How so?
Well, to know the exact brightness, the outgoing radiance of point A on a digital object, you have to add up all the incoming light hitting that point from every single direction.
Okay, that makes sense.
But that incoming light is just reflected light originating from point B, and to know the light coming from point B, you need to know the light that hit it from point C.
Oh, wow. It's exactly like standing in a hall of mirrors.
That is a perfect way to visualize it.
Yeah, because, you can't calculate the reflection in mirror A without calculating what's in mirror B. But mirror B is just reflecting mirror A ad infinitum.
What's fascinating here is that a computer simply cannot process an infinite loop like that.
Right, it would just freeze.
Yeah, attempting to calculate the exact, pure mathematical solution would cause the system to run out of memory. Or, it would literally take until the end of the universe just to render a single frame of a video game.
So if doing the exact math is completely impossible, Both of these fields obviously needed some kind of elegant cheat code.
It did. And the breakthrough, the solution to escaping this infinite maze was rolling the dice.
Randomness.
Exactly, randomness. Since exact calculation is impossible, both fields turn to random probabilistic trials.
So for Google, this was the random surfer model, right?
Yeah. Instead of trying to mathematically balance every single link on the internet at the exact same time, you just imagine a person.
A very bored person who is just mindlessly, randomly clicking links forever.
Right. And an authoritative page is simply one that has a really high probability of being visited by this random surfer over a long period of time.
The blog post mentions this brilliant conceptual breakdown from the Yuru Computer Science radio show to visualize this. They use Shinjuku Station in Tokyo.
Yes, that's a great analogy. Shinjuku Station has high authority, not just because it has a lot of train tracks physically built there.
Right, it's about the flow.
Exactly. Statistically, it constantly has massive crowds of people naturally passing through it. High traffic organically equals authority.
Okay, I buy the Shinjuku Station analogy for physical foot traffic. But how does a search algorithm actually see that traffic if it isn't literally tracking real human beings clicking their mice?
It doesn't track real humans. It simulates the probability of that traffic.
Oh, okay.
It builds a massive mathematical matrix representing all the links.
Okay.
Then it calculates the long-term probability distribution of where a hypothetical surfer would end up if they just clicked randomly for eternity.
So it's a statistical approximation. That actually explains the remote islands analogy from the source perfectly.
Oh, right, the mutual links.
Yeah, like if two totally isolated websites build a link between each other, they're technically connected. But if no outside traffic ever finds a path to either site, their overall simulated traffic stays at zero.
Which is why mutual link manipulation completely fails. Two spam websites linking to each other a million times won't boost their rank.
Because the random surfer is never going to naturally stumble onto that isolated island in the first place.
Exactly. So Larry Page solved the internet maze with a random surfer. Now, taking that conceptual leap over to computer graphics, the equivalent is the Monte Carlo method.
Brought to Practical Maturity by Eric Veach, right? Also in 1998, coincidentally.
Yes. Instead of tracking the infinite bounce of every single light ray, the engine just sambles random directions.
So in path tracing, instead of calculating all incoming light at a specific point on, say, a digital coffee cup, the software just casts a few random rays.
Right. It averages the incoming light from those random directions and follows each sample direction recursively to build a plausible light path.
It's like if you wanted to find the average temperature of a massive auditorium, measuring every single cubic millimeter of air is impossible.
Totally impossible.
But if you just take 10 random temperature readings from different spots and average them out, you get a number that is incredibly close to the true average.
That's exactly it. You use random sampling to approximate a calculation that is otherwise completely unsolvable.
But wait, if we only sample a few random directions of light, won't the final image look like grainy, static-filled garbage? Random dots of light don't look like a smooth shadow.
You are absolutely right. The raw output looks exactly like old television static.
I knew it.
It's incredibly noisy because a few random samples might miss the main light source entirely, or they might hit a really bright reflection by pure chance. The pixels fluctuate wildly.
So how does a video game ever look good?
The rescue comes from a fundamental mathematical theorem called the law of large numbers.
Oh, right. So as you simulate hundreds or thousands of random light paths per pixel, that random noise just fades away.
Exactly. Think about rolling a 6-sided die. If you roll it twice, your average might be a 2, which is totally skewed.
Yeah.
But if you roll it 10,000 times, the average will settle perfectly at 3.5. In rendering, as you increase the samples, the chaotic noise mathematically converges into a physically correct, photorealistic image.
So rolling the dice basically turns an impossible infinite loop into a solvable probability problem.
Exactly.
But, I mean, that introduces a whole new problem, doesn't it? What happens if our random surfer or our random light ray gets trapped in a closed loop?
Yeah, escaping the infinite maze isn't always clean. Cyclic references are a massive vulnerability in both of these systems.
Because on the internet, if that random surfer clicks their way into a ring of spam sites that only link to each other,
They'll never leave.
right, they just click in circles forever, which would artificially inflate the authority of that spam ring infinitely.
To fix that, Google introduced what's called a damping factor.
It's like a teleportation cheat. Right?
Basically, yeah. At any given step, there is roughly a 15% probability that the surfer just gets bored, ignores the links on the page, and teleports to a totally random new URL somewhere else on the internet.
Just to keep the system moving.
Exactly, it breaks the cycle. And path tracing requires a remarkably similar escape hatch. In CG, we call it Russian roulette.
That sounds a bit intense for a lighting algorithm.
Well, consider a highly reflective 3D environment, like two mirrors facing each other.
Oh, right. A randomly traced ray of light could just bounce back and forth between those two mirrors forever.
And that loop would completely stall the rendering process. So, to prevent this, path tracing uses Russian roulette to probabilistically terminate light paths.
It just kills them.
After a certain number of bounces, the engine literally rolls the dice to decide if the light ray dies or continues. It kills off rays to save computational power and prevent the system from getting stuck.
Hold on, let me stop you right there. If we just randomly kill off light rays to save processing time, doesn't the final image get artificially dark? We are literally deleting light from the room.
This raises an important question, and answering it requires us to look at a concept called unbiasedness.
Unbiasedness.
Yeah, the software isn't just carelessly deleting data. To maintain a physically accurate image, the overall energy has to remain perfectly conserved.
Okay, but how? If you delete light, you have less light.
The source text uses this really elegant casino analogy to demonstrate how this works. Imagine 100 players sit down at a casino and they each start with $1,000 in chips.
Okay, so the total money in the room is $100,000.
Right. Now, they play a game of pure Russian roulette. There is a 50% chance a player loses absolutely everything and goes down to zero.
Ouch.
But there is a 50% chance they win, and if they win, their money is doubled to $2,000.
Okay, wait, let me do the math on that. Half the players lose everything, so 50 players have $0.
Yep.
The other 50 players win, so they have $2,000 each. 50 times $2,000 is still $100,000.
Exactly.
The total expected money in the casino hasn't changed at all. So does that mean the rendering engine artificially boosts the brightness of the surviving light rays?
Yes. If a ray survives the Russian roulette probability check, its light contribution is mathematically multiplied to compensate for the ones that were terminated.
Oh, wow.
The individual rays behave radically differently, but the system-wide expected energy stays perfectly balanced. The room doesn't get darker.
So what looks like a rough, messy shortcut is actually mathematically precise global accounting.
Exactly.
The structural similarities here are just staggering. But honestly, the timing is the wildest part of this whole deep dive.
The 1998 miracle.
Yes. Larry Page's PageRank paper, which basically mapped the architecture of the modern internet, and Eric Veitch's PhD thesis on Monte Carlo light transport, which defined modern computer graphics, were both published in the exact same year, 1998.
Two researchers in completely different domains working on completely different goals, and they scaled the exact same mathematical summit at the exact same time.
And that summit is the concept of Markov chains.
Right. A Markov chain is the invisible skeleton holding both of these fields together.
We really need to break down how a Markov chain actually works for you listening at home, because it's the key to everything.
Well, simply put, a Markov chain is a stochastic model describing a sequence of possible omits, but its defining characteristic is its memorylessness.
Memorylessness.
Yeah. The probability of transitioning to any particular state depends entirely on your current state. It completely ignores the past. It doesn't care how you got there.
Okay, to visualize this without the heavy mathematical jargon, imagine dropping millions of little metal balls into a giant pinball machine.
I love this analogy.
Right, so as the balls fall, they hit this complex maze of pegs. And at every single peg, the ball bounces left to right based entirely on probability.
And critically, the ball doesn't remember the previous peg it hit. Its next move only depends on where it is right now and a roll of the dice.
Exactly. Now, if you keep dropping millions of balls through this pinball machine, eventually the number of balls piling up in the different bottom pockets starts to stabilize into fixed proportions.
And in mathematics, that stabilized end state is known as the stationary distribution.
Right.
The profound realization of the 1998 miracle is that the web-linked graph of the entire internet and the light reflection model in a 3D video game scene are both just incredibly complex versions of that exact pinball machine.
Here's where it gets really interesting. PageRank is basically throwing millions of simulated surfer balls into the pinball machine of the web graph.
Yes, and the long-run probability of where those balls accumulate, that stationary distribution, literally defines a page's search rank.
And path tracing throws light particle balls into the pinball machine of a 3D scene.
Exactly. The way those balls distribute after millions of memoryless stochastic bounces determines the accurate pixel radiance.
They're just asking the exact same question. If we let probabilistic transitions continue over a network, what mathematical distribution do we converge to?
That's the secret. The time spent by random walks equals statistical importance on the web, and randomly traced paths equals statistical radiance in a video game.
That is just, it's beautiful math.
Yeah.
But, we've been talking entirely about 1998. The blog post we were analyzing was written in 2026.
Right. Things have changed.
Drastically. We are living deep in the AI era now. I mean, Google search doesn't just rely on basic PageRank probabilities anymore. It uses massive neural networks for semantic understanding.
It tries to interpret the actual meaning behind your search, not just the links.
Exactly. And the graphics industry has seen a similar paradigm shift. Modern games use incredibly powerful AI denoising. The text specifically highlights NVIDIA's DLSS 3.5.
Which uses deep learning to reconstruct ray-traced lighting.
Right, so instead of waiting for the law of large numbers to slowly average out all that static from random sampling, AI can just look at a few noisy pixels and instantly guess the correct photorealistic image.
It hallucinates the answer.
Yeah, it bypasses the need to calculate thousands of bounces. So, has AI just rendered all of this beautiful 1998 math completely obsolete?
If we connect this to the bigger picture, the underlying mathematics are actually more vital than ever.
Really?
Yes, AI has not replaced the math, it's just a highly sophisticated shortcut. Neural networks are incredibly adept at removing noise or guessing context, but they possess no inherent understanding of physics.
Or authority, for that matter.
Exactly, they have to be trained.
Right, an AI model can't guess the correct answer unless someone gives it the answer key first.
And that answer key is called the ground truth. No matter how smart AI gets, the mathematically perfect standard used to train these massive models still completely depends on the pure algorithms from 1998.
So AI only knows what accurate global illumination looks like because it studied millions of perfect, mathematically converged images generated by Eric Feach's equations.
Precisely. And AI only understands web authority because it trained on the perfect PageRank graph mapped by Larry Page. The foundational math hasn't been replaced, it's just been hidden deeper inside the architecture.
Wow. That brings us to the end of our deep dive today. We started with the sheer impossibility of self-referential math, trying to solve a hall of mirrors using brute force.
Which didn't work.
No, it didn't. Then we saw how both Google and computer graphics embraced the magic of rolling the dice with random sampling, relying on the law of large numbers to find the truth out of pure static.
And we uncovered how they avoided getting trapped in infinite loops.
Right, using teleporting surfers and the casino math of Russian roulette. All of this culminating in that remarkable 1998 miracle where navigating the internet and simulating the physics of light were revealed to be identical mathematical siblings governed by Markov chains.
It's a really powerful reminder that human knowledge isn't just a series of isolated silos. Fields that look completely disconnected can converge into one coherent, universal system of logic.
I want to leave you with a final thought to mull over. If figuring out how light bounces off a coffee cup uses the exact same hidden mathematical skeleton as finding the best pizza recipe on Google, what other completely unrelated areas of your daily life are secretly governed by the exact same invisible rules?
It makes you wonder.
It really does. Are the traffic congestion patterns in your city mathematically identical to the way blood pumps through your veins? Is the stock market using the same hidden probability math as a flock of birds flying in formation? Next time you look at two things that seem totally disconnected, look a little closer. The math might just be identical.